So first, what does this group mean? So we call it developer technology or dev tech typically. And our main job is really two aspects. The first aspect is to help application developers to get best possible performance on NVIDIA platforms. And that typically means three things. First is when we have access to the source code, we would optimize the code either in a code level or in an algorithm level. And sometimes that involves changing the algorithm to fit better on the GPU. But also sometimes we don't have access to the source code. That's very typical when we work with a private company. And then we may do some reference implementation based on research in the papers. Or we may develop a library that the user then can directly call. In the case of reference implementation, then they will take our reference code and integrate themselves, adding their secret source, typically. And sometimes we're also developing some tools, typically providing tools to help performance analysis. And the area our group is working on are mostly two categories. The first one is HPC or scientific computing. And that typically means those different domains. First, the supercomputing centers like Oak Ridge, Livermore, Argonne. And typically, the things we do for them are two kinds of things. First, when a place like Oak Ridge or Argonne want to buy a new generation of supercomputer, they will release something called RFP, request for proposal. And within the RFP, there are a bunch of benchmarks. And in principle, all the vendors will submit result of those benchmarks on their future platforms. And then in principle, whoever has the best performance for those benchmarks would win the deal in a simplified word. So our job for that aspect is to optimize those benchmarks. And then we will project the benchmark performance after we optimize it on future architecture. And hopefully that'll be better than all the competitions. And we'll help NVIDIA win this deal. And once we win a generation of supercomputer in those centers, then we would do something called the COE, Center of Excellence. That's the name, where they give is where we, as a vendor, will partner with the top applications the center choose to optimize those applications, prepare them for the upcoming supercomputers, and also continue working with those teams while the supercomputer is operational. So those are two things. And the oil and gas, those are typically oil and gas companies doing seismic processing or reservoir simulation. Life science are things typically like drug discovery using molecular dynamics, or healthcare or bioinformatics for gene sequencing, things like that. Weather, climate, weather forecast, and climate prediction. CAE, that's computer-aided engineering. So this typically refers to things like using fluid dynamics or structural dynamics to simulate things like cars or airplanes, so people can design better cars or airplanes. And EDA stands for electric design automation. So those are the software people use to design chips like CPU or GPU. And there's a lot of computation involved because there are just so many transistors in modern chips. So it is a very computational heavy problem. And finally, somewhat funny, quantum computing is also very heavy workload people typically use on GPU, where they are using GPU to simulate quantum computing systems. And because it's typically various tensor operations in quantum computing, that's why GPU is a natural fit. And etc., a bunch of other things. And of course, all of you know we are in a middle of an AI revolution, maybe AI explosion. So a significant member of my group is working on AI, primarily optimizing for large language model, and some recommender as well. Yeah, I just want to say the money and brain power, I think, investing in AI from across the globe is so much that I think it will be a pity if you don't utilize AI in some way in your research. As a data point, for example, in the latest H100 GPU, the typical scientific flop, double precision, is 34 teraflops, something like that. But FP16, the typical flop people use for deep learning training, is 2 petaflop. So about 60 times higher than the scientific flop. And the INT8, the typical flop people use for deep learning inference, is a 4 petaflop, so about 120 times higher than double precision. So if you own a H100 and you don't use those deep learning flops in some way, you are putting a lot of things potentially wasted. Of course, AI is not a solution to everything, but wherever it fits, you can benefit a lot from using that in your research, hopefully. And another aspect of my job is we will then collaborate with the hardware and software teams within NVIDIA to improve current and future platforms. What that means is that because we work primarily on applications, so we would work with the hardware team to design the next generation of GPU because engineering is about trade-off. So we have a lot of what-if questions when we design chips. What if we increase cache by that much? But then that means something else has to be cut down. So the natural question is, if we do that, how does that affect the key applications NVIDIA care about? So we would do study with architecture team on those what-if questions. What if we increase that? What if we increase this? How does the application performance change? I think in academia, the fancy word for that is co-design. So we actually do a lot of co-design. The way we work with software team is typically, of course, when we run into bugs in compiler and library, we will file bugs. But also a lot of the library we develop for customers initially in DevTech would transition to the software team to become a product that other customers can leverage. So we work with them on productizing those libraries. Furthermore, NVIDIA now is developing a lot of domain-specific libraries, for example, cuLISO, cuQuantum. We, as a DevTech, is not only do dev taking for external customers, we also do dev taking for those internal software teams. So whenever our library team thinks something needs to be optimized, we're also dev taking for them. So we will help them optimize performance as well. So that's another thing we do with our software team. And I want to give you some example of the actual projects I worked on, but especially I want to highlight how these things I learned in KIPAC relates to those projects. So I want to talk a little bit about the work I did while in KIPAC 14 years ago. So I did mainly three things. First, develop a new AMR adaptive mesh magneto-hydrodynamic solver with sync particle algorithms in this code called ENZO. And then we use that code to do some MHD simulation of star and galaxy formations. And the third project is the main reason I then end up in NVIDIA is then we ported those code we developed on CPU to GPU clusters. Since we are KIPAC 20th, I want to talk a little bit about the history of that project. So I think it's the end of my first PhD year, 2006-ish, where Tom, in one of our many one-on-one meetings, he told me, I have this crazy idea of doing fluid simulation on GPU, but it was 2006, so there's really nothing I can use other than this thing called OpenGL. So Tom gave me a very heavy book telling me, go look it up. There is an example about using shader language to do n-body simulation in that heavy book. So of course, as a graduate student, right, especially first year graduate student, I was super excited. Then I go back to what the advisor told me, study that book heavily. But my conclusion is that if I were to use OpenGL shading language to port ENZO, I may need to delay my graduation for a very long time in the future. So we kind of shelved that project back then. But in 2000, I think end of 2007-ish, where CUDA 1.0 was released, and then Ralph, I don't know whether Ralph is here today, Ralph Kaler, who is now a research scientist in Slack, he told me about CUDA, and he actually did a first port of the hydrodynamic solver in ENZO to CUDA and got a very nice speed up. So I was really get excited. But back then, I was still busy with the second and the first project. So we didn't pursue it even further to port everything to make it production quality. But at the end of, I think, 2008, so under my third year, I was looking for another project, and then this become the end of that project. So we ported the MHD solver and also enabled the code on multi-GPU so we can run GPU cluster because we think that's really fancy back then. But the problem is that there was really no GPU cluster in KIPAC. But in order to write a paper, we need to demonstrate some multi-GPU scaling. So that was the GPU, I think the first GPU cluster in KIPAC. So 4 Mac Pro PC, I think in the Wiz lab, we found 4 of them, each with a Quadro card. So we interconnected them with Ethernet, built a Mac GPU cluster and demonstrated linear scaling on up to 4 GPUs, and looks very nice. And of course, linear scaling because I was writing really crappy GPU code back then, so it computes very slowly, but so of course it scales very nicely. Yeah, so Enzo, this code I worked on has those are the main ingredients: adaptive mesh and finite volume solver for the fluid and MHD, multi-grid solver for gravity, and particle methods for dark matter and sync particles, and finally retracing-based radiation transport. Especially those three are highlighted in green. I think those really covered almost, I would say, majority of the projects I then went on to work in NVIDIA. So KIPAC really prepared me very well for almost anything NVIDIA throws at me. So I will choose some examples from those three algorithms. And of course, retracing, I guess, goes without saying, GPU use a lot of retracing. So that's another thing. I guess I don't even need an example to convince you it's useful in industry. So the first one, finite difference and finite volume. I think one, of course, it's almost any scientific code will use some finite volume difference or element solvers. But the one prime example where I think finite difference really matters is all that matters is for oil and gas companies where they're doing seismic processing. So the seismic processing problem is something like this. The oil and gas company, they will short some wave on the surface of ground because they don't know what's underground and they want to find oil. And they can, of course, cannot dig up the ground. So they show some wave into the ground and then collect the reflection of the wave. So that's all the information they have. And then they want to know, do we have oil under this ground or not, based on the reflected wave. So the way to find out is by, now you know the boundary condition, then you solve a 3D wave equation, try to match with the received boundary condition. And in that process, you can reconstruct what the underground looks like. So the core is a uniform grid, high order, finite difference solver. And it's typically, I think, 8th or 9th order. That's a starting point for them because wave equation is, you need very high precision to get the wave speed correct, which is all that matters here. And here, the approach we took was that because those are oil and gas companies, so their RTM code, which is the name of this wave equation solver, they consider that as their trade secret. So we don't have access to the code. But all those companies, they like to show off their achievement in their algorithms. So they actually do publish papers on their algorithms and actually detail their papers very well because most of the people working on those projects are computational mathematicians who like to publish. So basically what we did is that then we took the paper published by every company and then we implemented RTM on GPU based on their paper. And then we go talk to them, hey, this is the algorithm you published and this is how fast you can run it on GPU. And that ended up convinced a lot of them to use GPU. And then we come up with a suite of RTM's kernel that, we just use that as the main vehicle of, and then this turns out to be one of the earliest domain where GPU computing was successful because of this reference implementation approach. So for the multi-grid solver used in gravity for Enzo, I think a prime example of linear solver in industry is industrial design using fluid dynamics. For example, you want to design a car, and so you want to compute the drag coefficient of the design, and you use something like ANSYS Fluent to compute that. And the most time-consuming part of those fluid code is the linear solver for the pressure equation. And the nice thing is that it's a linear solver, so anything you offer that solves X equal B would be good enough for them. So you don't really need their proprietary algorithm per se. And in this case, some of them did share their code with us, but it turns out it was a very CPU sequential code because AMG algebra multi-grid code, the solve phase is very parallel. But the setup phase is a very sequential phase to build up this hierarchy of grid. So that's the main difficulty point. So in this field, the approach we took is actually we assembled a small team of not just dev tech engineers, but also a bunch of computational mathematicians. We hired from the best AMG researchers in universities to really design something from the ground up. So we first designed a GPU shootable parallel algorithm for AMG, and then we implemented them on a GPU. And it was the best performing AMG library, I think even today. and then we give the library to Fluent and all the ISVs want to use and try to convince them to integrate that. So that's how we made some of those fluid code working on GPU. Yeah, library called MGX. Actually, I forgot why it's called X. Yeah, I guess as Elon Musk shows, anything is cooler with an X. So maybe it's a. Yeah, so the final example I want to give is a particle method we use in sync particle. And this is also the method used, for example, in drug discovery, where the problem is that you have a small orangish molecule, that's our drug, and you have this large blue molecule, that's our protein in our body. So the way drug works is that those small drug molecule will interact with the protein, and you will once it's docked successfully, it will change the behavior of the protein, and then so with a proper change, it will cure diseases. So they want to figure out for a given design molecule how that will dock to a particular target protein, and then they do molecular dynamic simulation to find to study that. And the algorithm really is very similar to sync particle like we use in astrophysics. In sync particle, we have a short range where we do a boundary accretion for the things near us, and then we merge with other sync particle when they are close to us. And of course, it also interacts long distance gravitationally with all the other particles. Here, you have short range van der Waals force with the nearby atoms, and long range electromagnetic force with all the other particles. So mathematically, it's very similar. And in this area, the approach we took is because most of the leading molecular dynamics code are open source science code. So we can work directly on the code. And when we do partner with all the major molecular dynamics applications for almost the past 14 or 15 years or so, because this is also one of the earliest domain where GPU was successful. And then we ported all of those code to the GPU. Yeah, so I want to summarize. I think it's really one thing. I think the skills I learned in KIPAC were really widely applicable in a lot of industries. And I guess that's not really surprising because in KIPAC, by definition, we are studying the universe. So we are capable of working on anything under the universe. So I think that's expected. So thanks very much.
Okay, so we have some time for questions now. Go ahead. Tom. And then there's one thing. Yeah, go ahead, Tom. A second microphone. And we can relay the question if you want to go ahead, but okay.
Well, when Tom's asked a question, I feel like my defense come back.
Yeah.
That's the hard one I didn't dare ask last time. No, I'm kidding. Can I ask you about pseudospectral methods? Is there sort of wide applications that you come across?
Yeah, so because pseudospectral method is kind of a really high precision numerical method. So some of the oil companies, that's one example, based on their experience of philosophy, they really prefer the infinite precision of a spectral method based on FFT primarily. So even like 10th or 16th order is not good enough for them. That's one example. Another one is some of the code we saw for nuclear reactor simulation, where they're simulating turbulence and they require really high precision. So they're using spectral element method. So that's some, so that's like a per element level they use as a spectrum method in some flavor. Yeah, I think those are two primary domains I can think of right now.
Okay, and there was a question at the back. Yeah, there. And then if we can get another, oh, you can.
I just had a quick question about the ENSO code that you wrote. How generic is it? Would it be able to be used for like doing solar, like like sun, to try to study like sun magnetic or the magnetic fields and such?
So first, ENSO is a pretty, I think, general community code. So it's open source with like dozens of authors. But the fluid code, when I was working, is mostly for inviscid order equation for large scale fluid. So it doesn't, which I don't think applies to the fluid for sun, which I think viscosity and things like that, and the imperfect non-ideal MHD effect are important. So I don't know whether Enzo has anything like that today, but when I was working on it, it really just do ideal supersonic MHD.
I see. Okay. Yeah. Thank you.
I don't know, Tom, do you know whether Enzo has new capability like that?
Yeah, for the sun, very often, if you want the whole model of the sun, the sound speed is so fast, you need really an implicit code to evolve the whole model. If you just wanted to model the atmosphere, like over short timescales, then even something like ENSO, you could make some progress, or like a short timescale phenomenon, you could get a first idea. But so it depends very much of what aspect, do you want a long-term integration, study the dynamo of the sun, is very different than studying a short event in a sunspot. So the latter, you might be able to do something, but the former, our code would not be able to do anything. Oh, good.
I had two questions. One is, you mentioned at the beginning kind of the leap the CUDA 1.0 was over OpenCL. I learned CUDA when I first started using GPUs, which was later than you. But I'm wondering, sort of in the modern era where we have PyTorch, TensorFlow, QPy, all of these nice wrappers, do you think it's still worth teaching students CUDA, or is it maybe better just to get them going to start with the Python wrappers? That's question number one. The quick. Okay.
Okay. I think to start with, definitely be more productive for them to start with something like PyTorch or JAX, because that's higher level and get them started doing science quicker. But once they really go into the woods of tuning their code, because all the backend of PyTorch JAX is written in CUDA. And especially if you want to use some layer that's not supported in PyTorch yet, then you have to write a CUDA custom plugin. So I think, it's really still worthwhile even now teaching them CUDA, because they're doing science, right? So by definition, it's something new. So by definition, it could be something not in PyTorch yet. And so they have to implement some secret source for their research. So I think CUDA can be still useful for those custom layers they likely will encounter.
Okay. And the second question is, you alluded to on the H100s that the floating point 16 and floating point 32 is so much higher throughput than floating point 64. I just wanted to ask your opinion of, I've also found that's actually true for the RTX 4090 and the other sorts of cards. The big thing that sets them apart is they have less RAM and less floating point 64, but they come within a factor of a few of the H100 for the lower precision. And they cost so much less that if you have a finite amount of money and rack space, you can get way more petaflops with those cards if you don't need the RAM. I was just wondering, as someone who's like thinking about building up GPU resources and only needs to do those sorts of operations, like, is there a reason to go for the H100s if you don't need the RAM or the floating point 64?
Okay, yeah, that's a tricky question. And I think if you just really, your use case can be all limited to a single GPU, probably a 4090 can be good enough for you. I think the value of H100 really comes in when you want to do multi-GPU training where your model is big. So then the NVLink connection between GPU will really make the scaling much better. And also the memory is bigger. So if your model is bigger, but if your model is small enough to fit on a single GPU, I think 4090 is perfectly fine for your job, I think. Of course, sorry, one additional point is that if your training can run weeks, then maybe a server grade GPU will still be better, because a gaming PC grade GPU, your job may die after, say, 2 or 3 days, and that could be a problem.
Okay. And other questions? Roger.
This feels even more like defense.
Yeah. Okay.
Every past director is going to ask you
you didn't know. No, it's great. It's a rather different question, and it probably doesn't have a good answer. And that, but you worked with NVIDIA for a long time. You've employed lots of people. You've had lots of colleagues there who've come as students or postdocs and so on. obviously NVIDIA is one enterprise, and obviously you're employing a lot of it right now, I'm sure, but what qualities do you look for when you're taking students or I don't know, possibly postdocs? What makes for success in a company like NVIDIA amongst the people who come into it from the universities as graduate students, say? Can you sort of point to something that they really, qualities they really ought to have or experience they ought to have?
Okay. So in particular, in my group, actually, because we work on those application optimization stuff, so I think the majority of the member, or at least more than half, is actually coming from non-computer science background, because the knowledge on both domain and parallel programming is important, at least in my group. So typically, we like someone with parallel programming experience, not necessarily CUDA or GPU, can be CPU or MPI. Also, I guess in particular in my group, it's just a general interest in performance optimization, and then correspondingly computer architecture would be the things we mostly ask during interviews.
Yeah, great. Yeah, and what I was really hearing there is domain expertise and something other than just CS,
Mm-hmm.
Great. Another question, yeah.
You probably alluded to this earlier, but you mentioned that you did MHD simulations on galactic phenomena. So how did that transfer over to now you being a principal engineer at NVIDIA? So, were you designing or developing the AMGX or just the MHD fluid simulations? How did that transfer over? If you could just speak about that.
So I think the primary things that I learned in those projects was how to write finite difference, finite volume code, understand how the algorithm, the basic mathematical pattern in those algorithms. And then when you work on parallel computing, that's really the number one thing you need, is to understand the mathematical pattern. So I guess, yeah, then there's a lot of domains once you work on them, they have the same underlying mathematical pattern. So once you work on something like MHD, then many other domains, you can very quickly understand their algorithm and how to parallelize them, because they are very similar mathematical pattern. Yeah, so I think that's why those three things that I mentioned in Enzo almost prepare me for anything that I saw later in industry, because not specifically the same algorithm, but the mathematical pattern is very similar. So you can wrap up on them very, very quickly once you saw them and understand them. Yeah.
Okay. So if I can ask a very basic question, this is like the opposite end of the spectrum from Kevin in terms of knowledge about GPUs, et cetera. But so I learned a lot from what you described, that you're often taking a problem or an algorithm, implementing it at NVIDIA, and then optimizing the NVIDIA chips for that. Mm-hmm. And so what do you modify in the hardware so that it's optimal for a particular problem? Is it at the hardware level that you're ever optimizing, like for a particular industry or big customer?
It can be in several levels. So some problem we really optimize just on a code level, so just write the code better to utilize the existing GPU features. Mm-hmm. But in some area, when it becomes big enough, like ARM, we really then go all the way to explore what changing hardware can make this particular transformer model run faster, because we know it can sell so many GPUs, and then the next generation of GPU would design something corresponding to those studies. Right. So it can be various level, depending on the project.
Thank you. Great. Mm-hmm. Okay, I think we'll move on then. So, one more, Steve, go ahead. We don't get to hear very often, so we want to get the questions in.
I'd just be interested to know, how does the volume of business of the type you described here compare to the volume associated with video gaming for NVIDIA?
So right now, data center is like, so the past quarter was 13 billion, and the data center was a majority of that. So gaming now is like 20-30% of data center. Yeah, we got a long way. Yeah, I think when I joined, the whole thing was like, let's say 100 million. So it's about 100x increase. Yeah, in the past 15 years. Yeah, definitely quite a progress.
Great. Okay, let's thank Peng again for the
All right, thank you. Okay.